let's look at how we can use numpy to quickly do some linear algebra calculations for us. So I'm going to start in my terminal, and I could actually do all of these calculations in my terminal if I wanted to. And actually, when I need to calculate something quick, like the inverse of a matrix or something like that, I usually just do it in my terminal. So we'll start there. First, I'm going to want to activate the EEX245 conda environment just to make sure that all of the packages have the right versions. And then what I'm going to do is I'm going to launch the Python interpreter, which I can open just by typing Python, and then I need to import numpy as np. And right here I can do lots of things, which I'll demonstrate for you. First, let's define x to be a matrix, which I do so by using np.array and then pass it a list of lists. Why don't we make it the matrix, I don't know, 1, 2, 3, 4, 5, 6, okay? When I ask for it, it formats it nicely, and why don't I say y is np.array 0, 1, 10, okay? So x is 3 by 2, which I can determine, or I can ask for programmatically by asking for its shape attribute, and y is 3 comma nothing, which means it doesn't have a second axis, okay? What are some operations I can do? Well, the first operation to know about is matrix multiplication, which we implement using the @ symbol. The issue, as we will see when we try and multiply x and y, is that x and y can't be multiplied directly, right? X has 2 columns, but y is 3 by 1, though it looks like a row vector here. And what that means is you can't multiply x and y. The dimensions don't match up, and we get that exactly back in this value error. One thing we could do is multiply the transpose of x with y. How do we get the transpose? A quick way to do it is by using x.t. x.t multiplied by y gives us back a vector with 2 things in it. Okay, so that's one way I could do something quickly. What if I want to quickly find the inverse of x transpose x? The inverse of a matrix can be found by using np.linealg.inv, and then x transpose x might look something like that. Okay. What else might I want to do? I can find the rank of a matrix using matrix rank. I can find the determinant of a matrix using np.linealg.det. Now, x doesn't have a determinant, which it'll tell us because it is not a square matrix, but x transpose x is a square matrix, and that works fine. And something else I might want to do quickly is figure out the optimal w star vector when I am trying to approximate y using linear combinations of x's columns, as we've done in this class. And there are several ways I can do that, and let me demonstrate some of those ways. The first is I could say w star is np.linealg.inv x.t at x at x.t at y. This is a direct translation of the formula that we've seen, and that gives me back my optimal parameter vector. Okay. What are some other ways I can do it? Well, as we talk about in the notes, the quicker or better way of doing this is to instead of directly inverting x transpose x, I should tell numpy to solve the system of equations x transpose x blank, or our parameter vector, equals x transpose y. That's a system of d equations if x is an n by d matrix. And so the way I do that is by saying np.linealg.solve x.t at x, comma x.t at y. And again, we like this because inverting a matrix is needlessly computationally expensive and prone to errors. And this gives us back the same thing that, where was it? Here, this did. Okay, so that works as well. There's also a np.linealg.least squares, which is another name for what we are doing. There, you don't even need to pre-calculate x transpose x and x transpose y. You can just give it x and y, and it knows what you're talking about is this act of projecting y onto the column space of x. And there, the first argument you get back is that optimal w vector with some other numbers as well, okay, which you can learn about if you open the documentation np.linealg.least squares. Okay, and here we see that that is returning back the sum of the squared errors or residuals, the rank of the matrix, and the singular values of the matrix. Here, little a is the matrix. We'll talk about singular values later on in the semester, but the sum of the squared errors being 10.66667. How can we verify that that's the case? Well, why don't we take our x and our w star, which we found, and multiply x by w star. This gives us the projection of y onto the column space of x. And this is actually y. So how do we find the errors? Well, it's y minus x w, so y minus x at w star. That's a vector with errors. What is the sum of these things squared? Well, I can square them. Well, let's do that step first. Let's square them. Oops, that should be a w star. Now I have all of the errors squared, and if I want them summed, I can take the sum of this array. And do I get the same number that I had up there? Indeed, I did. It said the other number was the rank of the matrix X, and X is indeed a rank 2 matrix. So those are some ways that you can quickly calculate things here in NumPy. The last thing I'll note is that to take the dot product of two vectors directly, you can use the function np dot dot. So like, maybe I want to take the dot product of the first column of x with y. The way you get the first column is by using this indexing notation, where here you specify which rows you want, comma, which columns. And so here I want all of the rows, so I'm going to put a colon, comma, just column 0, and that's going to give me 1, 3, 5. Similarly, if I put like 2, comma, -1 here, that's going to give me row 2 and column -1, so it's going to be the last column. So this is just going to be the number 6. Anyways, if I want just the first column, I do that, and I can dot this with y, and that's a perfectly legal operation. And as we might expect, that is the first thing we get back when we do the product of x transpose with y. Okay, so those are just some matrix operations that you can use NumPy to help you with. Again, you don't need to do these in your terminal. You could open a Jupyter notebook and do those commands there. You could also open your VS Code and do those commands there. But these are just various ways that you can quickly calculate stuff we might need to calculate in this class.